we have learned the mathematical induction, and now we will see that now there is another form of mathematical induction which is also very useful to solve many other mathematical problems, which is the strong form of mathematical induction. So, if we remember the principle of mathematical induction, there we have assumed that if we have to prove the formula for some value, then the immediate predecessor value or immediate predecessor statements is assumed to be true. Now, the main difference from the normal mathematical induction and the strong form of mathematical induction is that here we assume that not only the immediate predecessor statements, but the for all previous or preceding statements must be true. So, first we write the principle of strong form of mathematical induction. So, suppose we have a propositional function. Function say Sn in the domain of discourse is the set of positive integers. We put one restriction that set of positive integers greater than or equal to n0. Now, suppose that for first we see for n equal to n0, that means Sn0 is true, and for all n greater than n0, if Sk is true, for k where n0 less than equal to k less than n, then Sn is true. Then we claim then Sn is true for any value of n greater than n0. Now, we first see the difference from the simple mathematical induction. So, first the basis step, this is our basis step. We have considered the general value that n equal to n0. n0 can be 1, but we take some other value. We can take also that some other value of other than 1. And then for all n greater than n0, if Sk is true for k n0 less than equal to k less than n, that means this is my inductive step, and here we assume that all preceding statements are true. That means I can write the inductive state, we assume the truth values or I can write truth of all preceding statements. So, this is the main difference from the normal form of mathematical induction, where we have assumed only the immediate predecessor statements to be true. And many times these strong form of mathematical induction are very useful to prove some complex problems. Now, we see some of the examples and how actually strong form of mathematical induction can be utilized. So, we see one example. Show that the postage of ₹4 or more can be achieved by using only ₹2 and ₹5 stamps. So, first we have to show the basis step. Now, here before writing the basis step and the inductive state, we try to explain that what will be our approach that to use the strong form of mathematical induction. See, since ₹2 stamps are allowed, ₹2. So, if any n minus 2 postage it is true, that means any n minus 2 postage can be achieved with ₹2 and ₹5, then what we can do? We can just add another stamp of rupees 2 and we will get the postage of rupees n. That means, if this is my proposition, say proposition is Sn, that Sn is the say proposition of that postage of rupees n. Postage of rupees n can be achieved by rupees 2 and rupees 5 stamps. Now, if we assume that Sn minus 2 is true, that means that Sn minus 2 is that postage of, this is postage of rupees n minus 2 can be achieved by rupees 2 and rupees 5 stamps. Then we will simply add rupees 2 more. So, we add stamp of rupees 2 and we will get Sn, and Sn can be achieved or Sn is true. So, this is our approach. So, that means it is very simple. If we consider or if we can see that Sn minus 2 is true, then we will add each time only rupees 2 stamp and we will get for all values of n it is true. Now, say if it is 5, say n equal to 5, then our n minus 2 is 3. So, but our statement is not given for n equal to 3, or say if n equal to 4, then n minus 2 is 2. So, it is not given. So, particularly for n equal to 5, so our statement for this n equal to 3 or n equal to, it is not given. The statements are only rupees 4 or more, So, here our n0 is, that means our basis step, that n0 is equal to 4 and 5. We have to show separately that the statement is true for n equal to 4 and n equal to 5. So, this should be our basis step. So, now we see the proof. So, our basis step, so for n0 equal to 4, we need rupees 2 stamp. For n0 equal to 5, we need 1 rupees 5 stamp. So, postage of rupees 4 and rupees 5. So, postage of rupees 4 and rupees 5 can be achieved by using rupees 2 and rupees 5 stamps. So, our basic step is true. So, our SN0 is true. Our basic step is true. Now, what about our inductive step? Already we have seen that strong form of induction, that all preceding statements are true. So, assume Sn is true for all preceding statements or all preceding values of n. So, it is true for n minus 2. So, Sn minus 2 is true. So, once Sn minus 2 is true, add rupees 2 stamp and make Sn be true. So, it is proved. So, one Sn minus 2 is true, we will just add rupees 2 and Sn is true. So, it is proved that any postage of rupees 4 or more than 4 can be achieved by stamps of rupees 2 and rupees 5. So, this is proved. So, notice for this particular example, it is very much required that some preceding values, like for n we have that Sn minus 2 must be true. Okay. Now, we say different type of examples, that how mathematical induction can be used to compute the complexity or the number of steps, because that is very important in computer science. So, we see a different type of example here. Suppose we have we insert parenthesis and then multiply n numbers. So, we have to multiply n numbers, say A1, A2, A3 up to An. And we insert parenthesis and then multiply the n numbers. Say for example, n equal to 4, I have the numbers A1, A2, A3, A4 and the multiplications are of A1, A2, say A3, A4. So, we insert parenthesis and first we multiply A1 dot A2 we multiply A1 dot A2 and then A3 dot A4. Say this is A1, say this is capital A1 product, this is capital A2 and then I need another multiplication. So, to multiply phone numbers, so to multiply phone numbers, we need 1, 2, 3 multiplication. Now, prove that if we insert parenthesis in any manner whatsoever and then multiply the n numbers then the number of multiplications are n minus 1. That means to multiply A1 into A2 into A3 up to n minus n, we have to perform n number of multiplications. And if we insert parenthesis and we multiply two numbers at a time. Now, we see the proof. So, first is our basis step. So, for n equal to 1, I have only one number A1, only one number A1. So, the number of multiplications is 1, which is equal to number multiplication is 0. 0, which is equal to 1 minus 1, n minus 1. For n equal to 2, the numbers are a1 and a2. So, the number of multiplication is 1 equal to 2 minus 1. So, the basis step is true. So, we can write that it is basis step is true. That means, for n equal to 1 or n equal to 2, the multiplication is n minus 1 is true. Now, for inductive step, say I have n numbers a1, a2, a3 up to an. So, now we put parenthesis, we first partition into 2, a1 we multiply a1, a2 up to t, at and at plus 1, at plus 2 up to an. Now, if we apply the strong form of induction, then t is less than n. First thing is that we partition or we insert parenthesis, so that t numbers we multiply and rest n minus t numbers, these are t numbers and these are n minus t numbers. So, here t less than n as well as n minus t also less than n. So, if we use the from strong form of induction, mathematical induction, right? The proposition is true for all preceding statements, true for all values less than n. That means, it is true for t and n minus t, since t less than n and n minus t also less than n. Since we have partitioned or we have inserted the parenthesis, so that t numbers are multiplied in one part and rest n minus t are multiplied in another part. So, if we continue the inductive step, we can write that the number of multiplications the number of is, for the first part it is, since t numbers are there, so t minus 1 multiplications are required, plus for n minus t, for n minus t minus 1 multiplication of required, and the last multiplication I need another one. So, this is for t number of multiplications, or I should write multiplication of number of multiplications for t numbers and this is for number of multiplication for t minus n numbers, and this is for number of multiplication for last two product. So, this becomes n minus 1. So, it is proved. See, this is number of multiplications. So, similar way, what we given a program or some computations like that, this is a multiplication. So, what will be the number of computations required, number of multiplication, number of additions or number of comparisons, which actually directly gives the complexity of a program. So, or complexity of some algorithm. So, using strong form of mathematical induction, sometimes it is very easy to compute the complexity of some algorithm or of some program. We have one small thing, that it has, we have read the simple or normal form of mathematical induction and the strong form of mathematical induction. Now, if we read the well ordering property, which is actually the generalized concept of both of this form. So, I just mention or write this property. Now, it is the well ordering property. The well ordering property of non-negative integers that state that every non-empty set of non-negative integers has a least value. And this is the generalized, this simple statement is the generalized form of the normal mathematical induction and the form of normal mathematical induction as well as strong form of mathematical induction. So, I can write generalized form of both the forms of mathematical induction. Only I mentioned that this well ordering property, this is mainly used to prove our well known that quotient reduction theorem. That quotient reduction theorem it is used, and the theorem that if a positive integer n is divided by d, that means if n and d are integers greater than 0, then there exists q the quotient and r the remainder that satisfy n equal to qd plus r, where 0 less than equal to r less than d, and furthermore that q and d are unique. Furthermore, q and d values are unique. So, this is our very well known quotient reduction theorem, and this is when it is proved by very easily, it can be proved by well ordering property. But all of we know this simple form, just I mentioned that we can prove this thing by this mathematical induction. So, with this we finish that concept that how mathematical inductions are used to prove the many mathematical formulas.